Hi everyone, it's Miss Basega. If you haven't used one of these review packet video resources before, then stop right now. Here's what you need to do before you watch this video. At this point, you should have already done all of the problems, or at least tried all of the ones you can. You should have already checked the key and highlighted things that you might need extra help on. And then don't watch this whole video from start to end, only watch the parts that you're struggling with. That'll save you some time. So let's get started. First off, number 1. In this case, this is a vibration around an equilibrium point, and simple harmonic motion only occurs when the restoring force is proportional to displacement. Now, think about this in terms of a spring. The more you stretch a spring away from its equilibrium point, the larger the force trying to hold it back. The farther the distance x, your displacement, the more the spring force tries to bring you back towards equilibrium. The spring force is the restoring force, so as x goes up, force goes up, and that causes the mass to move back towards the equilibrium point. For number 2, a mass spring system oscillates with simple harmonic motion because of its elastic potential energy. You could have also written spring energy here. That would also work. Because think that when it's in this position, it wants to go back towards equilibrium, at which point it will have the most kinetic energy possible. Now, number 3, be careful on this one, because it says the spring pendulum moves a total of 28 centimeters. So I'm going to draw this on this picture up here. So one complete cycle is one movement to the left plus one movement to the right. And the amplitude would be one measurement of the distance from equilibrium to max on either side. So notice I'm putting little marks here indicating congruence. So if my object started and I released it from rest here, boing, it would accelerate to the left, stop, and accelerate back. If this has to add up to 28 centimeters overall, this must have gone 14 to the left, then 14 to the right, making the amplitude 7 centimeters. Tricky, tricky. So now I have a longitudinal wave. A longitudinal wave has a series of compressions and rarefactions. So each stretched region, that's this section right here, must be some sort of rarefaction. A rarefaction is a section of a longitudinal wave with lower than average pressure, indicated in this case by the wave fronts being farther and farther apart. Or my bad, the slinky coils being farther apart. So now I have two sound waves passing through the same medium. Get your highlighter out for a second. If they have the same medium, what do they have the same of? They automatically have the same speed, the same wave speed. So our two sound waves are traveling the same speed but have different wavelengths. They must have different wavelengths because there are different frequencies. Use our wave equation for this. They have the same speed. So if they have different wavelengths, they must have different frequencies. These are inversely related. They obviously aren't different types of waves. They're both sound waves. The amplitude doesn't affect either frequency or wavelength. And the nature of the medium, they're going through the same medium. So it's definitely C. For number 6, I'm going to draw a 2-meter long stretched rope fixed at both ends. And it's going to produce standing waves that split this 2-meter long rope up into harmonics. So in this case, the first harmonic would be, let's put in L is 2 meters, and N is equal to 1, the first harmonic. The first harmonic would be 4 meters long. So D, check, is produced by this string. It would be this pattern. Let's see the second harmonic. 2 times 2, the length of the string, over 2 for the second harmonic. Well, one possible harmonic is 2 meters long. That would be the second harmonic that looks like this. The third harmonic would be 2L over 3, so 4/3. Ooh, that is not one that's on the list, so all right, keep going. The next wavelength up would be 2 times L over 4, or 1 meter long. So it looks like so far all of them have worked except for C. C must be the one that does not get produced by this pattern. Okay, but we're going to keep drawing because number 7 is about the nodes and antinodes of the third harmonic, so I might as well keep to the same pattern. The third harmonic would be 3 complete antinodes, 3 complete up and downs. But how many nodes is that? That's 1, 2, 3, 4. And in a guitar string, this would represent where you put your finger, and the other would represent where the bridge of your guitar is. And both of those form nodes because the string doesn't move in those locations. 8. Sound waves are longitudinal waves. 9. The region of sound where the density and pressure are greater than normal is actually just the opposite of question 4, which we just answered, right? Rarefaction is the low pressure section, so compression is the high pressure section. On this picture, the density would be represented by having more coils per area than the rarefactions. Now, when you listen to a sound, we hear its note or its pitch, which is an example of how humans observe the frequency of sounds. Now, the amplitude is kind of proportional to loudness, and I put a little kind of here because it depends on human sensitivity. There are some frequencies we're more sensitive to than others, so we might hear 2 sounds of identical amplitude at different loudness if we're not sensitive to one. For instance, you could put a dog whistle as loud as you want, and I will never, ever hear it. So many pages. Okay, in general, sounds travel faster through solids than anything else. So how about we go with sounds travel faster through solids than gases? That's because sound is a longitudinal wave, and in order to travel, its particles need to collide with each other, and this happens faster if the particles are bonded together. 12 is asking about the Doppler effect. The train is moving towards the observer. So if our observer is here and the train is moving towards them, then 1, they should move, and 2, that makes the wave fronts close together up front. Short wavelength, high frequency. The person that's sitting on the train hears the same frequency that the horn's actually putting out. So the sound from the train as heard by the observer is higher in pitch, that is higher in frequency, than the sound heard by the passenger on the train. This unit we didn't get a chance to talk about timbre, so it's probably not that. Hint, guys, if you haven't seen a word before, it's probably not that. Right? We know it's not the same because there's relative motion, and there has to be the Doppler effect in this case. So between higher or lower, I would draw out my picture to figure out shorter wavelength, higher frequency. This person would hear a higher frequency. And they should probably also move. Okay, Doppler effect occurs with all waves. All waves experience the Doppler effect, just like all waves refract and reflect and transmit and absorb. When the frequency of a force is applied to a system and matches the natural frequency, this is called resonance. When you push a person at a swing, you push them at the natural frequency that the swing wants to oscillate at. That makes resonance because it makes their amplitude go higher and higher. That's why in a swing you can't just kick randomly. You have to kick with a specific beat. For 15, the wavelength of the fundamental frequency is twice the length of the string. We know it's not A or B because the fundamental frequency is special. The fundamental frequency only represents half of a wave. Remember, a wave is one complete up and down, and this is only one up. The wave gets finished all the way out here. All the way out here. So that is 2L, and if you'd like to try this out for yourself equation-wise, 2L over 1 equals 2L. The wavelength of the first harmonic is twice the length of the string it's on. Finally, the quality of a musical note of a certain musical instrument results from its combination of harmonics. Some of these just don't make sense, guys. 16, an instrument, one musical instrument, cannot have multiple fundamental frequencies from the same tone. The fundamental is only the first frequency, so you can't have more than one of those. Sound is not a transverse wave. And they all have the same speed because all of the sounds produced by your instrument are going to travel in the same medium, and the medium changes the wave speed. For 17, at A shows one wave with positive amplitude and one wave with negative amplitude. A must show destructive interference. But at D, both of the waves have an amplitude in the same direction. To be fair, that amplitude is both down, but that is still constructive interference. They make a wave whose amplitude would be larger in the negative direction than either one of those combined. In fact, if we math this out right here, red has an amplitude of negative 2.5, blue has an amplitude of negative 2.5. When they get added together, they would make an amplitude of negative 5. Number 19, spring pendulum. Whenever we see a picture and we recognize it as associated with an equation, we should probably just write the equation down. The equations are there to help us shortcut so that you don't have to memorize all the relationships. We can simply look at the equation and see there that if the spring constant is increased, that would make it time period divided by a larger number in the denominator. Dividing by a larger number makes it smaller. And then I can come up with a justification after. If the mass is increased, that would be like multiplying by a larger number, so that would increase the time period. Oh, and none of these things in this equation have to do with amplitude. So that can't change the time period. So now let's go back and do some justification. I use my equation to figure out the pattern, but now let's explain it. Having a more massive object means it's harder to pull back and forth, harder to vibrate this object. Think of it as like the heavier object has more inertia. Harder to vibrate, heavier object. As a result, it goes slower. And since it goes slower, it takes more time. More time means larger time period. Mass goes up, time goes up. Heavy objects move slower. But if K goes up, why would that make it go faster? Well, that would go faster because the spring constant is larger. This is a stiffer spring, and a stiffer spring is capable of a larger restoring force. And if you pull with a larger force, that makes an object go faster. So K is bigger, spring force is bigger. Larger force makes this oscillate faster, and a faster oscillation means less time. So if k goes up, time period goes down. It's not exactly an inverse because of that square root, but they do affect each other in this way. And the amplitude of the pendulum doesn't change the time period at all. It doesn't show up in the equation. It wasn't a relationship when we plotted in our graph. When we plotted it originally, when we did this lab, right? We dropped it from different positions and saw that it took the same time pretty much no matter what. So, in this case, let's take a look at the other type of simple harmonic motion. Both of these are simple harmonic motion because both the spring pendulum and string pendulum have some sort of restoring force that wants to return an object to equilibrium. For number 20, this is a long, 2 meter long cable with an 8 kilogram bowling ball. And if you're not in the habit of drawing pictures when it's not given to you, you should do that. Because if I look at this picture now, I associated it in my brain with this time period equation having to do with the time period of oscillation of a pendulum. So let's calculate. That's 2 pi square root of L over G. L is the length. G is 9.8. I had somebody the other day ask me, can I put in, do I need to put in 8 times 9.8? Do I need to put in the number of newtons? We did that a lot back in the day. But the answer is no. G is your gravitational field, your regular, just straight 9.8 value. So this gives a time period of something like 2.84 seconds. Frequency is inversely related to time period. And if you're a person that's still struggling to figure out when do I use what equation, by all means, write down the other equations with frequency in them. This one doesn't apply because that would only be for harmonics of a standing wave. So we know that's no good. We know this one doesn't apply because that's the wave equation, and a pendulum is not a wave. It is a repeating motion, but it is most certainly not a wave. So, frequency then, I know the time period. This is the frequency equation I can use because it's the only one whose values I know. Notice that's just a number 1 on the top. No units, no nothing crazy here. So this would be 1 divided by 2.84, and that gives a frequency of something like 0.35 hertz. And if you want to double check your logic here, this means that each oscillation takes 2.84 seconds to go there and back again. So in 1 second, it only travels through part of this motion, a fraction of a there and back again, a fraction of this cycle. So I should have a fraction of a frequency, a fraction of a hertz. Okay, just like in 19C, amplitude doesn't affect period. It doesn't show up in the equation. And this is only true for small angle oscillations. So in this case, we figured this out in our lab. For small angles, for theta less than about 15 degrees, time period doesn't depend on amplitude. Similarly, do you see mass in this equation anywhere? If the mass is doubled, that has 0 effect on this value. We found in our lab that if you change the mass, it does literally nothing to the time period. So if the mass is doubled, nothing. No change. So how would I make the frequency of this higher? To make the frequency higher, remember this inverse relationship here. Frequency higher means time period down. If this is a faster oscillation, each one should take less time. This equation suggests I have 2 options. In order to take less time, I could have a shorter string, or, okay, ridiculous one, or a larger gravity, a larger gravitational field. If I brought this to Jupiter or the sun, or Saturn. It would be very bad, but it would have a larger gravitational field and it would oscillate with a larger frequency in a smaller time period. There are no other changes you can make here. So be careful you didn't say increase the mass, and you didn't say push harder, and you didn't say increase the amplitude. None of those changes affect the time period. Time period for the small angle approximation depends only on length and gravitational field. So then, slinkies. In order to make a transverse wave, and imagine you're watching this from above, right? In order to make a transverse wave, we had our slinky. And I'm drawing out the grid of the floor right here, so you imagine we're watching it from above. And let's say I had person A. There's their smiling face. And person B. There's their smiling face. In order to make a transverse wave, person A took their hand and moved it back. Sorry, let's go up and down. One tile. That produced a transverse wave pulse with an amplitude of 1. That wave would travel down the slinky, would travel down the slinky, reflect off the barrier, and bounce back. In order to make a transverse wave pulse, the amplitude, the direction that this person moved their hand up and down. And as a result, the wave traveled to the right. The amplitude is perpendicular to the velocity in order to create a transverse wave pulse. And remember, when we did this in class, how I help us remember this is transverse is perpendicular. Capital T looks just like that symbol. And similarly, longitudinal. Longitudinal has those two L's. Parallel. A transverse wave has amplitude perpendicular to velocity. Longitudinal wave is parallel. So how would person A move their hand here? Person A would take their hand and move it right and left in order to create a wave. And since this is a wave pulse, we're going to only show one section of really high compression as opposed to it repeating over and over like normal. That longitudinal wave would travel from person A to person B, reflect and come back. In order to make this wave, they moved their hand parallel to the direction of velocity. The wave traveled to the right, the person moved their hand right and left, parallel. Question 22 is asking us to relate wavelength, frequency, and speed. If you're a person that often gets stuck on what equations work, let's do our knowns and unknowns. The frequency is 600 hertz. The wavelength is 0.57 meters in air. So we want to relate that to the speed of sound. We're trying to find the speed. Put a little box around the speed here. So I need some equation that relates frequency, wavelength, and speed. And that is the wave equation. Knowns and unknowns. Equation, now let's substitute. Wavelength is 0.57. Frequency is 600. That puts the speed of sound in air as 342 meters per second. So the technicians now place this buoy in seawater where the speed of sound is faster than in air. Now we want the frequency and wavelength as it goes into this new medium. Notice this wave went from air to water. It's changing the medium, so it changes the speed. When it changes the medium, it changes the wavelength, but it does not change the frequency. So let's do our knowns and unknowns for this problem. We know the speed, that's 1500. The frequency also stays the same. It's still the same 600 hertz sound. Think of it as like this buoy is making this sound, whether it's out of the water or in the water. find the new wavelength. Right. So to find wavelength, I need to relate wavelength, frequency, and speed again. So wave equation, substitute, divide by 600 on both sides, and solve. So that's 2.5 meters. So let's check this for a second. As it goes from air to water, refraction occurs. That's a change in medium. Accompanied with that change in medium is also a change in wavelength. When the speed is low, the wavelength is small. When the speed is high, the wavelength is big. We will come back to that repeatedly in light, so don't forget it. Wave basics. So you should be able to draw all sorts of things about waves right here. Amplitude is the distance from equilibrium to the crest or equilibrium to the trough. So let's draw all those amplitudes out here. One wave is one complete up and down. So I can draw a wavelength from crest to crest. That's what I prefer. That's what I usually draw, though I guess you could also do from trough to trough or from equilibrium to equilibrium point, all the same. So if each picture represents 1 second of time, which has the longest period? Well, if each one is 1 second of time, then wave B completes 2 cycles in 1 second. And wave A completes 1, 2, 3, 4 cycles in 1 second. Thus, wave A's period is 1/4, or 0.25 seconds. And wave B's period is 1/2, or 0.5 seconds. The wave with the longest period is wave B because it takes the longest amount of time, half a second, to complete 1 cycle. Oh, in which case, perhaps maybe I should have asked D first, right? The one with the higher frequency is the one that completes more cycles in that 1 snapshot of time. More cycles per second was A. It completed 4 cycles in that 1 second of time. So wave A has a higher frequency than B, thus B has the longer period. Okay, day 2. So we should have finished about that much in day 1 of studying. That way you don't overwhelm yourself. You should probably split things up. It helps with comprehension. Now we're on to part 2. Question 24 is the standard model for Doppler effect. And there's 2 observers, A and B. And the car is doing the thing that it was doing in the video, right? The person is honking the horn and driving past observer A and observer B. Observer B hears the highest frequency, and observer B hears the highest frequency because as the car approaches, that means its compressions, these crests here that are being denoted by the wavefronts, have a shorter wavelength. And because they have a shorter wavelength, they have a higher frequency. Person B is hearing a higher note than person A. Okay, well, I guess then this is just the opposite. Person A has the lower frequency because they have the longer wavelength. Lower frequency. The thing they have in common, however, is it's sound in both cases, and the speed of sound is 340 meters per second in air, no matter what source is making that sound. So let's take a look at number 25. In the diagram below, we have a model for earthquake waves. The epicenter, or sometimes you'll hear it as like the focus, is where the 2 tectonic plates rub against one another, creating waves. And we have people equally spaced along the outside of the Earth here. We know that not everybody can experience the waves. I'm kind of skipping ahead, but person A and B experience both S and P waves. Person C experiences no waves. In class the other day, I was like, oh, I wonder what this is called, the place where there's no waves that hit it. Apparently, person C is in a place called the shadow zone. Wow, that's a lot cooler than the name I came up with. Shadow zone. This location at C that doesn't experience the S waves, the red, and doesn't experience the P waves, the blue, gets missed by both types of waves. D and E both experience P waves only. Great question. So, even though I skipped ahead, both S and P waves are felt by A and B, indicated by the red and blue. Only P waves are felt by D and E, indicated by just these blue here. And C. C is in the shadow zone. Sounds kind of spooky. Anyways, back in order. 25A. The part of the Earth with a liquid composition is this outer core here. And that's why at this boundary, the S waves get absorbed and no longer transmit through the boundary. At this outer core, the earthquake waves tell us that S waves can't travel through, and therefore this outer core must be a liquid. S waves can't travel through liquids because they need shear in order to travel. If the particles aren't bonded together, then one particle can't pull the other particle up. So, difference between S and P waves. So, first off, S waves are transverse waves. I'm going to draw them like this. And one of the ways you can remember is S transverse, looks like a sine curve. That leaves P waves as my longitudinal waves. P waves are waves that travel as a result of pressure, whereas S waves are a result of shear forces holding two particles together or adjacent particles together. P waves can travel through solids, liquids, or gases, can travel through any material medium, not a vacuum, whereas S waves can travel through solids only. P waves are also faster. And they're also faster, which is why they are called primary waves, because they strike first. If person B over here were experiencing this earthquake, first the blue longitudinal P waves would hit them first because they travel faster. Primary waves hit first. Then, with a delay in time that's proportional to their distance from the epicenter, B would then experience the S waves, which hit second. They're called secondary waves because they are slower than P waves. So, grouping all these terms together, you'll see that there's like this pretty sweet pattern here. S, sine, transverse, shear, solid, secondary, slower. It's like they're all S's, whereas P waves are primary waves. They hit first because they're faster. They travel because of pressure and can, as a result, travel through any medium. They're longitudinal waves. So, finally, we got to the end of the unit. We were dealing with standing waves. So, we all did this great lab where we had the different strings with different harmonics. And the first harmonic, that was an easy one. This is the one with one up. Then the wave hits the boundary and reflects backwards, interfering with itself, creating two nodes with one antinode. Now remember, the wavelength of the first harmonic is always longer than the string itself. So this value tells me that L is 0.6 meters, and the 624 must be the speed. I expect the wavelength for one complete up and down to be longer than the string for the first harmonic. So wavelength equals 2L over N. That's 2 times 0.6 over 1, or 1.2 meters. The frequency of the first harmonic depends on the wavelength, which we have, and the speed, which we have. Look at that. So that's 624 meters per second equals 1.2 F. So that F, dividing by 1.2 on both sides, gives me 520 hertz. Now, for the third harmonic, I expect a wave with a shorter wavelength and higher frequency with the same speed. So drawing this is a wave that has to have 3 antinodes, hit the other barrier, reflect back across the fixed barrier, and interfere with itself, making a pattern of 4 nodes, and 3 antinodes. But now the wavelength is shorter. Notice that before the wavelength was really big. Now my wavelength should be shorter. Higher frequency, shorter wavelength. And this frequency now, I can determine the frequency by taking my original frequency, my fundamental frequency, and the third harmonic should be 3 times as high. So 3 times 520 is equal to 1,560 hertz. Now, that leaves 2 choices. I could use that information to find wavelength using the wave equation, or I could use that length, because I still know the length, and substitute n equals 3 for the third harmonic. If I've done this right, and I'm pretty confident I have, those 2 values should give the same number. So 624 equals wavelength times 1560, or 2 times 0.6 over 3 should give me the same number. On the left-hand side, that's 624 divided by 1560 gives me 0.4 meters. I did expect that to be shorter than the 0.6 meter string length. And on this side, that gives me 1.2 over 3, or also 0.4. You can check either way. They should both come out identical. So when I change the tension in the string, the wave speed should increase. We know that the medium of a wave depends only on, the speed of the wave depends only on the medium. So changing the medium, that is the tension, changing the medium changes the speed, and therefore changes the frequency. But you know what it doesn't change is it doesn't change the wavelength. Now, why it doesn't change the wavelength is that, remember, the wavelength depends on the size of the string. Changing the tension doesn't change the size of the string, so my wavelength must still be 1.2 meters. You could think of it like this. When you tune a guitar and you increase the tension, what you're doing is you're increasing the velocity, but keeping the wavelength the same. Multiplying by a bigger number, having a larger velocity, means a higher frequency that you hear, because the size of the instrument stays the same. E is the opposite, however. The frequency that you hear depends on the speed over wavelength. So what if you change the wavelength? The wave velocity stays the same. I'm not tightening or changing the string in any way, so the speed, the velocity can't change. The wavelength of the first harmonic decreases because I'm making the string shorter. Imagine I put in a shorter string than this. If L is smaller, the wavelength is also smaller, so the wavelength is smaller. And as a result, dividing by a smaller number makes a higher frequency. And that's how we tune a guitar. So this lab then, We had two different methods. So if this one's not familiar from you, like you did the in-person lab instead of the one on the computer-generated simulation, this should take you through both. So in this case, a lab is set up with a speaker connected to a sine wave generator. The speaker is set next to one end of the tube that is open on each end. The first harmonic should have one complete antinode. So remember, antinodes on both ends because that's where the air goes in and the air goes out. The wave goes down, meets an open boundary, and reflects back. The first harmonic has nodes in the center, antinodes at the end, and it's one complete antinode. Right? So think half a wave plus half a wave equals one wave to make the first harmonic. So, to get our wavelength then, we know the length of the tube, and since this is the first harmonic, the fundamental frequency, I expect this length to be greater than the length of the tube. So that gives me a wavelength of 0.68 meters. We know the frequency is 520 hertz. And it's asking to find the speed. So 0.68 meters times 520 hertz gives us 353.6 meters per second, which is relatively close. We know the actual speed of sound in air is about 340, so maybe this room is just warm. It happens. So now the frequency is slowly increased. So imagine this speaker is now going frequency increasing until the next resonance frequency is heard. Now, just like when you were playing a speaker next to a wine glass, the resonance frequency would make the tube shake and vibrate, and you would hear that sound louder than other sounds as a result. The plastic prop, or maybe it's glass. Maybe this would break. Our boom whackers wouldn't break because they're plastic, but maybe if it's glass it would. So the frequency is slowly increased until this next loud resonance frequency is heard. The second frequency should just be twice the first frequency. Should be twice as high as the fundamental. The second harmonic should have a frequency that's 2 times 520, or 1040 hertz. Still completely within the human hearing range. Its wavelength, because remember, its pattern still has antinodes on both ends, would look something like this. Maybe a little bit prettier. 2 nodes, 3 antinodes. And the wavelength for this, I suppose you could calculate it if you want, but notice this is already one complete up and down, right? The wavelength of this should be equal to the length of the tube for the second harmonic. You could do the math for this if you like. 2L over N, where L equals 0.34 and N equals 2. 2 over 2, length of the tube, 3.4. The wavelength is equal to the length of the tube for the second harmonic. True for strings and tube instruments. Awesome. So that leaves this last chart and we're done. So our frequencies are multiples of each other. So that's 520, 1040, etc. And our wavelengths should be getting shorter and shorter. 0.68, 0.34. I had a student the other day look at this pattern and say, does that mean the next wavelength is going to be 3.4 divided by 2? And that's not quite right. Remember for patterns here that what you should be doing for wavelength is you should be taking your wavelength and applying the wavelength equation, 2L over N, which makes the third wavelength 2 times 0.34 divided by 3, and that's not equal to 0.34 divided by 2. Right? So our wavelengths should be getting smaller and smaller. But notice that this is not just like dividing by 2 here. Okay. Applying that equation repeatedly, we see that our wavelengths are getting smaller and smaller. And at the n equals 10, it's very small indeed. On the other hand, the frequencies should be getting larger and larger. 1560. And what I'm doing to get these, if you're unclear, is I'm taking the fundamental frequency and multiplying by 2, multiplying by 3, multiplying by 4, multiplying by 10. And just a fun fact, guys, these are all frequencies still within the human hearing range. The pattern I'm applying for the frequencies, our frequencies are multiples of the fundamental. And just for funsies, since you guys have the time, I suppose I have the time as well, remember that my third column over here, all these wavelengths and frequency products should be giving me the same approximate speed. So earlier, I had the speed calculated as something like 353 meters per second. Right. That value should be approximately the same for all the different data points. So exactly the same for harmonic 2. Pretty close for harmonic 3. And these might be coming from rounding differences. Right? So, best of luck on your all electronic assessment. Stay safe out there.